Okay, we're studying electrons now, and perhaps the most important thing to know in chemistry is all based on electrons. After all, the protons and the neutrons are locked up in that nucleus, and all their behavior is not chemical behavior, but nuclear behavior, things where atoms can transform from one to another. Not chemical behavior at all, not the kind of thing we need concern ourselves with now. So in terms of chemistry and chemical behavior, it's really important to realize that it's all about those valence electrons. I've set up this slide unlike others in that there's no need to take any notes at all. It would be tight to fit them in, so I really want you to just listen. Don't write the thing down. Just try to understand what's being said. This is one of the most important concepts in chemistry, so please pay close attention. We can learn how to predict the reactivity of all of the elements based simply on where those outer shell electrons are. And that's what we're going to do in this unit. The big idea is that all atoms want full outer shells, a simple concept. Now, of all of the elements, which ones do have full outer shells? That's right, only this group here. These are the only ones that are stable. Use those as a model. Assume that every one of these elements wants to become like those, and you can predict how things will behave. Okay, almost always that's 8 valence electrons. Perhaps the only exception is helium, which has a full outer shell when it has 2. 1s1, 1s2, 2 electrons, and it's good to go. All the other ones, by virtue of the way the shells fill up, will have 8 valence electrons. One complicating factor that may come up for some of these central groups is they may have unfilled inner shells. But for most of the elements of life and most of these elements in general here, this 8-electron rule will be valid. Neon. Note that there are 8 fuzzy electrons in this outer shell. It's stable. It's right there. It's a noble gas. This is a happy camper. This is a model to look at. Nice, stable molecule. You can eat it. Your body won't digest it. You can try to react it with anything. It won't react. You can make it glow, but that's just moving the electrons around into different shells. It's not doing any chemistry. It's a physical process. Sodium. Uh-oh. I see one lone camper here. This is an intensely unstable element. I've worked with it, and if you throw this stuff in water, you probably heard the stories. It catches fire. It's nasty stuff. You have to be careful with it. Strange, it's a metal, but it's a silvery metal with only the hardness of perhaps cold butter. Beautiful stuff, but notoriously unstable. It's going to lose that one valence electron to become just like neon. It will have the same number of electrons as neon. Therefore, we can say it is isoelectronic with neon. Fine. How about this guy? Chlorine. Count up those outer shell electrons, those valence electrons, and you'll see you're one short of a full deck. Chlorine, it's unstable. It's going to gain an electron. And note that that is a match made in heaven. Sodium will lose an electron. Chlorine will gain that electron. Ooh, it's got 8 now. They both have 8, and they are happy as is. Now, one important thing. That does not mean that the sodium cation is stable. You cannot buy a bottle of sodium cations. Likewise for the chlorine anion. But when they are together, they have a melting point of over 2,000 degrees Celsius. You can put a flame to them, and nothing will happen. Also keep your mind open to the idea that chlorine will gain an electron, but it could also perhaps share an electron. This will be the subject of another unit, and I just want to get you thinking in that direction. For sodium, it doesn't work. It's got nothing to share. It's going to lose one, but if it shared with another sodium atom, you got 2 extra electrons. It's hard to figure out how it's going to share. In any event, we can now predict the reactivity of all the elements based on this simple idea. Atoms want full outer shells. This first column, they all have, see here, 1 valence electron. This +1 means they'll all lose an electron, losing a negative charge to form a +1 cation. All these group 2s, they're also notoriously unstable in their elemental form. When people say you need some calcium, they don't mean calcium metal. No, they mean the calcium dication. That's okay. You're going to eat some calcium chloride. When they say potassium is in bananas, no. The potassium ion is in bananas. If there was any potassium in bananas, the bananas would explode. Anyhow, this middle group is more complex. It's true they'll all have 2 valence electrons, they'll all lose electrons, but it's more complex because they have unfilled inner shells. For now, just assume that these guys will lose electrons. A little simpler here, at least up on top for these group 3s that start with boron. They'll lose 3 electrons. Now here you are right at the cusp. These group 4s, carbon, silicon, etc., they're going to either gain 4 electrons or lose 4 electrons. Either way, they complete that outer shell or they gain a filled inner shell. So their reactivity is a little bit less predictable. There is another option that they will prefer to do, and that's the topic of another unit. The nitrogen group will prefer to gain 3 electrons. The oxygen group will gain 2. After all, it's easier to gain 2 than it is to lose 6. And the fluorine group, the halogens, have 7 valence electrons. It's easiest for them to gain 1, as we showed with chlorine. And here's our nice stable group here, the group 8s, the noble gases. All the reactivity can be based on the idea that they want to become like noble gases. Keep your eyes open, keep your mind open to the idea that all of these electrons here can be shared rather than gained or lost, and that's an option for these. These metals, no, they'll just lose them. Okay, that's how to predict the chemical reactivity of all the elements, and this is Screencast 5.0.